Dr. Gleason received her PhD in Earth and Planetary Science from the University of California, Berkeley in 2010. She joined Stanford University as a postdoctoral scholar in 2010, and then worked for Los Alamos National Laboratory in the Shock and Detonation Physics Group before joining the SLAC National Accelerator Laboratory as a staff scientist in 2018. Her work focuses on visualizing materials behavior and response across all length scales at the most extreme environments possible in nature, from depths of the Earth's crust to planetary cores and even stellar interiors. Her studies center on high-pressure mineral physics and planetary evolution from the atomic level up. In 2019, she received her Department of Energy Early Career Award from the Office of Science, Fusion Energy Science. So today's talk is going to be recorded, so if you're not comfortable with that, please log off. And also, if you have any questions, please enter them in the chat field, and I will read them at the end. And also, please be aware this is an unclassified meeting with many people logged in from outside the lab. So please be aware of any export control or classification issues. Otherwise, please enjoy the talk, and please take it away, Arianna.
Wonderful. Thank you so much, Paul. And many thanks to the organizers for allowing me to give this talk today. I see on the attendees many colleagues and friends, familiar names. So thank you guys so much for tuning in. Some of this you may have heard before, so apologies on any repeats. But I'm excited to take a different direction today. Majority of my work is focused on X-ray diffraction and looking at structural transformations of materials. But today I'd like to talk more about X-ray imaging and ultrafast X-ray techniques that look at the mesoscale sort of properties of materials. So thank you, and let's get going. So here's the outline. First, we'll talk about a few different X-ray imaging platforms that have been leveraged across facilities to pursue examination of materials at extreme conditions. And then we're going to talk about 2 or 3 different case studies I outline here. ICF ablator materials, I feel like I'm talking to the Pope here. You guys are a Livermore, Livermore lab is ICF essentially. So much of this is done in collaboration with different folks out at Livermore lab. So we'll talk about certain aspects of that, and then we'll look at a few geomaterials, and then even options we're looking at in astrobiology, which is really exciting, and then sort of outlook, what is the frontier of X-ray imaging for dynamic materials properties. So this essentially goes without saying, especially to this community, but materials matter, and lack of predictive capability, different length scales for dynamic response is really contingent on the heterogeneity of a material. And so here I show a couple graphics on the left side, length scale and time scale, and in different performance regimes across extreme condition examples, we see that different materials properties play a role in the response. And this has been studied extensively. In fact, I think some of these graphics are out of date. They're even more up-to-date 2020, 2021 reports that indicate the extent to which understanding materials response at extreme conditions is so critical. And probing the structure with X-ray techniques is one direction our community wants to go. And so here we bring together, in this talk and in other talks I'm sure you've seen, the opportunities for dynamic loading, generating an extreme condition, and then probing with a variety of X-ray techniques. Diffraction is essentially one of the lower hanging fruits. I'm not going to focus on that today. We're going to talk about imaging, and spectroscopy is another one that is certainly an area of active research. And the good news, I think, at many facilities, whether it's SLAC or Livermore or Omega, domestically and internationally. Our experiments are getting better and better, and they are rivaling the experimental fidelity that's required. But there's still microphysics. There's still questions that we need to address in a very specific way. And so we can do better, and we will do better. And that's part of where I'd like to conclude the talk at the end, and thinking about what opportunities we have to march this forward. So the experiments I'm going to talk about today involve the X-ray free electron laser we have here at SLAC. This is the Linac coherent light source. And just to give a brief reminder, the LCLS is unique compared to synchrotron radiation. And in fact, besides being particularly brilliant and very ultra short pulse widths of the order tens of femtoseconds, it's coherent. It has full transverse coherence, and that for imaging techniques across the board is incredibly advantageous, and we'll look at that in just a moment. So you're probably familiar with this sort of schematic shown in the right, lower right here, but the source, the coherence is essentially related to the source size, and the transverse coherence is sort of demonstrated in this way by virtue of the pinholes or single slit schematic. The longitudinal coherence is related to the temporal coherence, and that is effectively considered as our bandwidth. So these are the aspects that we're going to lean on when it comes to our unique probe here at the LCLS. And we might think of traditional imaging in a few ways, pair it back to our time spent using synchrotron-based imaging or sort of lab source. And we think traditionally maybe of certain lenses, so insertion of an optic in the beam to modify the way in which it focuses before or after a sample. And these are still certainly in use. We might think of different kinds of radiography approaches, some of which we're going to talk about today. But in the future, or the direction I think that some folks want to go, that we're realizing we can take advantage of, is this coherent property of the xFEL. And in particular, constructing density distributions in 3 dimensions. So really taking that next leap, not just having a 2D visualization of our process, of our dynamic material at a time slice, but moving towards 3D. And I think this is shown sort of in a schematic way how we're going to take advantage of that. You sort of have traditional, absorption near field imaging. Think about, when you go to the doctor and you have an X-ray done of your bones. Near field is more like phase contrast. A little further out, you can still do phase contrast imaging. But I think eventually the field, the community, we want to go to 3D. We want to go to 3D in a single shot so that we can visualize our sample response from any direction. And so I think moving towards holography and coherent diffractive X-ray imaging is what we want to try to do. And so this talk doesn't necessarily speak to specific examples here, but we're on the roadmap. So I think that's the part of the message. So CXDI, coherent X-ray diffractive imaging, there's different geometries, and this is a paper, a well-known review paper by Meow et al., and it's a nice graphic that shows a couple different options we've looked at so far at the LCLS. Certainly plane wave, coherent diffractive imaging, so you effectively aperture your sample. This is also done certainly at synchrotrons to improve their coherence. You can aperture down a synchrotron X-ray source. BLAG CDI is also executed at synchrotron facilities as well as here, again, by use of an aperture. This time, sample specification requires crystalline, notionally very small single crystal. Ptychography is an example we're going to look at in detail, and that could be any sample. Now we can branch out in terms relax sample requirements, but it requires quite a bit of overlap of the beam. You need to oversample spatially, and then all of these techniques, different optics can be inserted, and the requirement here is to finally realize the sample in 2 dimensions or 3 dimensions. We need to process the data using an iterative phase retrieval algorithm, and that's sort of demonstrated here. We basically take a Fourier transform, feed that back into the algorithm, and rerun this process until you come up with something. This also requires a set of priors, so some bit of information about the starting sample. But algorithms are becoming more and more robust. So I think that's another area where there's lots of research and investment in our community. So we're going to take these ideas of X-ray imaging and show some examples from the Linac Coherent Light Source. So we're your sister facility, neighboring facility across the bay. Most of the work that's been done, actually, well, I should say, is in this far hall, so down at the end, way at the end of the Linac, but also a few stations here in the near hall. And in the experimental touch, you might be aware, I know many of you on this phone call have actually used the Matter in Extreme Conditions instrument. Here's a schematic showing that. The MEC instrument has notionally 2 different types of dynamic drivers, a short pulse laser system as well as a long pulse laser system. Now, I'm not going to dwell on these other than, this is effectively a tool for us to generate high pressure conditions. I'm mostly using the long pulse laser, so we're generating a steady shock for several nanoseconds and then probing with the LCLS beam. And many of you on the call are also expert in this, using this instrument, so I won't dwell on that too much. Rather to say, the LCLS is trying to very much diversify and leverage unique operating characteristics, and I think a couple colleagues have even used this pulse train capability already, which is really exciting. Essentially, instead of a single pulse at a rep rate of 120 hertz, there are different ways to operate the guns such that we can have a suite of pulses, a pulse train, notionally. And the separation here is a pulse every 350 picoseconds. So fraction of a nanosecond, and to date they've demonstrated eight pulses in a row. This timing structure here is actually tunable. So if you had a dynamic process and you needed, two of your pulses closer together and maybe the latter further apart, this is possible. Moreover, the opportunities to change color, in other words, to modify the wavelengths between the pulses. Right now, this capability for so-called two-color or dual color is only in the order of hundreds of EV. So we're not at the KEV range yet in terms of this color, but you could, for instance, go above and below an edge. And use that to your advantage. So this sort of multi-bunch or pulse train operation has now been functional for a few runs. And like I said, I'm going to show some data here, and then also I believe others have taken advantage of this too, colleagues at Livermore Lab. So here's an example of an early experiment led by our detector lead here, Philip Hart. And these are cameras. Oh, so I should say, the xFEL is X-ray character is being modified here to send two pulses each 4.2 nanoseconds apart. But the other piece that's very strategic is the camera, right? So how do we not necessarily have superpositioning of diffraction or of the resultant image or other information? We need a detector that can gate or separate out each of these pulses from the LCLS. So we've also had an ongoing collaboration with Livermore and Sandia National Lab using their gated detectors, their Icarus and a family of detectors called the UXI, Ultrafast X-ray imagers. So here on the right-hand side is a graphic from Phillips' paper in 2019, basically showing X-ray heating of copper, and as we understand it, the first pulse is actually heating the copper, and the second pulse then probes that copper, and so we end up getting a doublet, peaks shifting in D-spacing, and that graphic is shown there. We've also tried to combine this with a separate pump, a very small optical laser, only a few millijoules, unfortunately. But we executed a similar setup, but this time pumping a gold foil now with this small laser, and we had a different suite of X-ray pulses, this time 4 in a row, probing the gold. So these operational parameters are available to you, and I'm going to show how we've also deployed them with the long pulse laser. So the heart of the talk here is focusing on this third diagnostic. I know we often talk about diffraction. Different kinds of spectroscopy have also been deployed. Certainly there's velocimetry that we need to include, but for the remainder of this talk, we're going to try to focus on looking at phase contrast imaging, moving towards density distribution in 2 and 3 dimensions. So a science application, which is very much well known, well studied. Like I said, I feel like a kid talking to the Pope here, talking about ICF. So inertial confinement fusion, and in general, considering fusion materials and the environments in which they encounter are harsh, and often the heterogeneities in those materials dictate the response, especially at extreme conditions. Shown on the left here is a simulation of an implosion for ICF, and the understanding is that notionally this should be, if all things are going well, a perfect sphere, spherical implosion, but we see these features that jet out, these spikes, and this is consequence of seeding and propagating forward hydrodynamic instabilities. Some of these, there are many different causes of these instabilities in the growth, but one that is considered in this community is voids and defects in the material. And shown on the right here is a radiograph of a diamond ablator used in a capsule, and you can see some of these features, not necessarily desirable aspects in the sample that could be potential seeds for these hydrodynamic instabilities. So we want to look at how does this process actually take place? Can we visualize step by step this void collapse? How does this pore and the surrounding material respond? What is the density distribution? Even insofar as seeing jetting, plasma jetting in the center of the pore. Can we visualize that? Can we have an accurate two-dimensional and then perhaps three-dimensional reconstruction of our sample in real time? So to do that, we're going to pursue experiments at different facilities, and in particular here at the LCLS. The imaging platform, as I've mentioned already, is one in which it has been used before, I should say, and takes advantage of focusing the xFEL in a particular way. The focus is actually upstream of the sample, so we're in a magnification geometry to do essentially phase contrast imaging in the sort of farther field. It's not truly in the far field, but we're close, and I should say the potential MEC upgrade certainly looks forward to a much longer larger detector distance to enable this a bit more. We can combine the imaging with diffraction simultaneously. I think that's a big advantage. So we have both pieces of information on a single shot, as well as velocimetry records. So this is the essential setup. I think I have one more schematic here. Part of what helps us out here are these small beryllium lenses that are used. They're compound refractive lenses of beryllium. They're about the size of a nickel. And sets of these lenses help us to focus the X-rays down upstream of the sample. So here's another schematic of the phase contrast imaging setup. One more promotion for MEC. In fact, proposals are proposal call has been announced. And if you wanted to pursue imaging yourself for any science case, my understanding is the phase contrast imaging setup, this exact design will be offered as a standard configuration in the coming call. Those proposals are due July 19, I believe. Okay, so some really pioneering previous work that has deployed this setup here, work by Andreas Schrapp and others. They looked at diamond. So a single crystal of diamond. So here are a set of phase contrast images at different time slices, and you can see in this fairly homogeneous sample of diamond, here's the initial shock front. There are some lens defects. This is effectively dust. Unfortunately, that's on the beryllium lenses, so that's unfortunate. But these features should be static. You can see we've got some third harmonic contamination here. That's this bright spot in the center of each of the images. And at different time slices, so these are each different samples now. So each time slice is a separate piece of diamond. This shock front moved forward, and then Andreas and others have looked at the density distribution across this front. I provide some notes and caveats here on sort of the gotchas in pursuing a technique like this. There are certainly some assumptions that have to be made. And I put this forward, these notes forward as areas where we can try to improve in the future. Because it's only going to get harder, right? This is a really simple case. You've got a well-known material, diamond, that's homogeneous, it's single crystal, so we don't have grain boundaries. Hopefully we don't have, I don't think any pore spaces or vacancies were identified. And we're just basically looking at the main shock. However, other colleagues' efforts have taken place here where we made the sample geometry very complicated. So here's some work by Richard Sandberg and others where they milled out a void in a sample and shock compressed that to look at void collapse. This is in an energetic material. So each of these images are pairs. So top and bottom is a pair in each time slice case. And each sample is different because we're in Richard's work here, we're not using the pulse train. And so you can see there's a number of interesting features, sort of hard to identify what's going on. We've got a few bright lines that show up. I think we've identified this is probably the main shock here coming through. The void is somewhat modified, but this is a messy case. Then followed by what we've affectionately referred to as the black fog, which is behind the main elastic and plastic waves here, and we think this is actually the ablation front moving through. This was done at a somewhat lower X-ray wavelength, I think 8 or 9 keV. So we've considered this in upcoming experiments so that we can actually see through this black fog. And the idea that we're pursuing is shown here on the left as a schematic. So we have our sample with our synthetic void, and we want to take advantage or have taken advantage of the LCLS pulse train and probe, 4 time slices in a single sample once we've compressed with the long pulse laser, so we get 4 snapshots, and then from analysis of these, reconstruct 2-dimensional density distribution. Okay, materials matter, like I said. So our focus here for an ICF study, ICF ablator study, we're working with colleagues at Livermore for beryllium. We've not yet completed any of the beryllium shots. We've got secondary containment protocol that we're developing here at SLAC in order to do that. Diamond, we've coordinated with Livermore and GA for diamond ablators, and then polystyrene in consultation with Livermore colleagues as well as samples directly from LLE. We're continuing to work on algorithm development, and then eventually the direction we want to go is single-shot, multi-image approaches. A little bit more on the samples. So some of these samples are, I've mentioned, are natural, like the diamond is a natural sample, or when I say natural, I mean the voids based on the fabrication process at Livermore and GA and elsewhere have features that we locate with the X-rays prior to shock compressing. Other samples, like the plastics, for instance, we make synthetic voids in them. I also have a test sample, a silica here. It's a bit easier to work with. And so we use femtosecond laser milling to generate pore spaces or voids in the sample. We've also pursued another fabrication method. So we're not actually using a polystyrene, but rather a photoresist plastic, essentially polymer, called SU8. Which is used in the semiconductor industry for different nanofabrication tools. But here the SU8 is actually our essentially our plastic, our material of interest, taking the place of polystyrene. And in it, I can place quite specifically a void. But this void is technically a hollow glass shell, and the wall thickness is a micron or less. So we include that in our rad hydro simulations, that it does have this wall thickness, but we are hoping this is a good starting place for mimicking a void in a plastic. Here's a side view of optical microscope photograph of placement of the void. So notionally the drive laser would come from left to right. No, what am I saying? Right to left, sorry, in this image. And so the drive lasers, in and out of your computer's, the X-rays are in and out of the computer screen as your eyeballs are looking at it, and then the drive laser comes here from the left side. And then we would watch the collapse of this void. So we've taken some preliminary data. We didn't quite get everything we'd hoped for in this first data set, so I'll walk you through what we did collect. So shown here on the left are raw data images. Here we've used the UXI, the Ultrafast X-ray imager from the Sandia and Livermore collaboration. And notionally the Icarus, I think Icarus 2 camera. And the shock wave here is moving from bottom to top in this image. This is a single sample, multiple slices or multiple X-ray pulses from the pulse train. And we can see that there's a compression of this void modification, and then we sort of encounter this black fog again. These data were collected at 8.2 keV. So we're not able to see through, to penetrate through this ablation front. I think the good news is that we will leverage harder X-rays next time, 18 to 20 keV, and have more success. You can see there's some maybe gentle compressive waves that run out in front here, but we're not quite at the pressures that are important for ICF. But as far as looking at how the different components are working together, we're making progress. Here's an X-ray aerial density simulation from colleagues at Los Alamos National Lab. And so once we're able to achieve much higher pressures, we can do a comparison to the density distribution as seen. And some of the really interesting features are at the edge or in the center here, these different curl-ups that have been discussed. Here's a synthetic radiograph of this at a certain time slice, and you can see some of these really cool curl sort of circular features here that develop. And so this is what we're looking for. This is the money shot that we eventually want to take and visualize in the data. So we have upcoming beam time that will take place in October to continue to push this forward. I did want to say, certainly make an acknowledgement of some other great work that's been going on, not at FLAC. This is work at APS, also focusing on void collapse, again in energetic materials, sort of similar to what Richard and others had been doing before. And the idea is, to again understand hydrodynamic instability formation and how that relates to the detonation process in explosives and other energetic materials. So this is work, I think that was done at HPCAT and at APS. So again, looking at the flaws in materials and the consequence. We have looked at a few other materials, not necessarily with the pulse train, but single shot and combined the diffraction, the X-ray imaging capabilities with diffraction. And here's a study from a student of mine who's now at Google. She's very successful, making way more money than any of us. And so here she designed an experiment on silicon. And similar approach, the focus of the beam is upstream, so we're in a magnification geometry, collected simultaneous diffraction, and really leveraged this nano or very small submicron focused beam to zoom in and look at different regions during the shock compression event. And I think in some of these zoomed in regions, you can even see, it's probably hard on your computer screen here, but there's quite a bit of cross hatching. In other words, some of the actual planes during the deformation process can be visualized, and we're working on looking at some of these subset data sets in more detail to actually look at this cross hatching of the lattice planes. But at each of these points in the compressive the passage of the compressive wave, then we can identify the structure, the lattice structure. So we collect this diffraction here, and we have all of this information on a single shot, which I think is really exciting. Okay, well, here's more on the silicon. I'm going to move along here just for sake of time. So far, what I've shown you is just a single orientation, interaction between one X-ray beam orientation and the sample. But work that has been done here and other colleagues also at Livermore, Stefan Haureg, Tom Pardini, and others have deployed in different locations and ways split and delay, multi-layer capabilities of steering the beam around, steering an X-ray beam around, so that you're actually crossing the target in different geometries. And so I think that's another direction we want to go as a community to build up a stereoscopic view of our sample. And now, just to be ambitious, or some other word you could choose, you could consider, the pulse train here in this context. And so now we could have a buildup of, this pulse train coming in, but we then insert our X-ray split and delay, or a way to steer the X-rays around to intersect our sample. And then we build up this incredible, essentially single shot sort of tomography or pseudo tomography view of what's going on to move toward 3D. And I think that's one, certainly one option we're all excited about pursuing. Here's another science case I wanted to introduce, where the imaging of the sample during compression is important. totally different science case than we've talked about so far, but consideration of prebiotic materials to biotic samples. In other words, potential origin of life studies in looking at void collapse or pore collapse, where meteoritic material undergoes compression during collision, and some of that meteoritic material could have fairly simple starting molecules included, and when those molecules break up, when these these materials break up into sort of radical components, different simple components, and then recombine, the formation of certain nucleobases is possible. And this has been studied extensively, actually, in abiotic work and modeling. And here is one study that focused on formamide, which is actually quite common, turns out, in interstellar clouds. Formamide is often found in the tails of comets, certain aspects of comets. And study that's been done looked at the breakup of this very simple formamide material into different radicals, and it turns out it's possible for it to recombine into all of the nucleobases of RNA, which I think is just phenomenal. But looking at the time scale of this process really at the appropriate ultrafast time scale has not been done. And so part of some studies we want to pursue here at LCLS is to actually examine this time scale. So previous work has been done using laser-induced dielectric breakdown of certain gases. And so here's the study, I think it was 2015. And they used the PALS laser to do this, and they did examine the spectra of the materials and sort of a sketch of the concentration of different components as a function of time. But it's at much longer time scales, which is still important. But I think our hypothesis is there's a lot of interesting dynamic chemistry going on here at the very short time scales, and we're going to be in a position here with LCLS2 where we can get at some of this dynamic chemistry. But the part here, I think, that is related to the imaging talk today is we want to sort of have all different diagnostics available. So X-ray spectroscopy, certainly for the dynamic chemistry, but also X-ray imaging to try to understand, if a surrogate meteoritic material is effectively backfilled with the formamide and during shock compression, can we visualize in 2D the consequence of that void collapse with all of those different components involved. So this is, again, sort of looking forward into the experiments we want to execute. So imagine this is the same image you saw before as a video, but now slice by slice we consider, a surrogate target that is a meteorite with formamide, and then we shock it and we look at what happens in the ultrafast timescale. So this is very exciting. I think it's all void collapse, right? The physics here and looking at hydrodynamic instability processes has applications that extend from fusion energy materials work, ICF ablator materials work, but then also in looking at origin of life studies. And I think that's really exciting. And so we're leveraging all of these different techniques to pursue a variety of science scopes. So here's just another example of bringing that all together, an origin of life science focus, combining the imaging with the diffraction, but then also having an X-ray spectroscopy component that is at the sub-picosecond time scale using soft X-rays, which I didn't talk about at all today, but that would be a different focus. The third aspect of imaging that I want to bring up that is relevant, maybe of interest to folks here, Livermore and in HED science, is leveraging ptychography. So this is an example, coherent diffractive imaging, and as we mentioned before on a previous slide, requires quite a bit of overlap, oversampling. You're effectively moving the sample around, and these arrows here indicate sample motion, and you bring your X-ray in, and you're looking at a diffraction pattern in the far field, and you raster, so you move your sample around in some pattern. And this is done, doing this at the LCLS is not necessarily a big deal. It's also done at synchrotrons and other locations, but we collect these data here. I think the one advantage of the LCLS is the coherence, over traditional synchrotron source, and more than that, we can take a single shot per position, so we can operate in a fly scanning mode because our temporal pulse width here is so short, rather than averaging or trying to de-blur at a different facility. So we've tested some of this two-dimensional, and we're working toward three-dimensional. Not quite there yet, but here are some examples that might be of interest. So we did this ptychography, and now we're executing in a few weeks, actually, ptychotomography. And here's a sample, again, in collaboration with colleagues at Livermore Lab, looking at different foams that are used, that are important for ICF capsule construction. So we've got a copper foam, that's this image here. And again, I think just to impress upon you, the images we get back, right, when we're executing this ptychography, right? They look sort of like this. So it doesn't give you any indication. We include no priors in our phase retrieval algorithm, but we get back, depending on the sample that we start with. So here's just a slice of the image for the copper foams. The exciting news is we're going to try this again in early August to have a three-dimensional reconstruction of a spindle of copper foam or tantalum oxide foam. And so that's another benefit. It's another direction we can go as a community. And now imagine doing this, but doing it in a dynamic sense, right? So maybe this is some aspect of a capsule or design of some material, and we want to orchestrate ptychotomography in a single shot. And I think we're getting there. Here's some other two-dimensional reconstructions. Here's a little cute LCLS. But the point is we're dependent on this still iterative phase retrieval as we've overlapped the beam on the sample. But we want to do better. We want to move towards single shot, right? So I feel like, building up over a suite of angles to get a tomographic view of a sample is possible, has been done, demonstrated at a synchrotron. We're working to demonstrate that here at LCLS. But looking down the road, how do we actually execute time-resolved, single-shot, coherent diffractive imaging? And so here are just a few snapshots based on, or a few ideas to help us consider this based on previous work. Time-resolved BLAG CDI, this is challenging because the samples they have a certain requirement to be very small, but nonetheless, time-resolved imaging has been done. I think time-resolved ptychography and ptychotomography, by leveraging novel X-ray optics, different pinhole arrays, Fresnel zone plates, in a certain way, perhaps made out of diamond, so it can withstand the intensity from the xFEL is going to be key. Testing these so that there's no distortion of the wavefront is going to be critical. But we're making progress, right? There's folks out there willing to study this in different ways. Here's another example of time-resolved ptychography, this time using a random mask by other colleagues here at SLAC. And so on and so forth. Some of these examples that I show here have only been demonstrated so far in the soft X-ray regime, which is unfortunate. But the problem is that technically, what's required here to do this at an xFEL for hard X-rays requires tremendous sample to detector distance. So there's a technical trade-off that we need to consider if we want to pursue, in-flight holography and hard X-rays. But I think we can get there, right? If we push forward as a community. So here, just in the spirit of discussion and comment, this was sort of partially a science talk or intro into some of the work being done here, but then also in technique and pushing forward on different X-ray imaging opportunities. And I think with that, I will conclude and ask if there are any questions, and thank you so much for your time.
Thank you very much for the lovely talk, and apologies again to everybody for the technical difficulties we had in the beginning. We hope to have those all worked out before the next meeting. We started the meeting in the older room without host capability, so we couldn't actually run the meeting. But there won't be a meeting next week, but in 2 weeks from today, I hope everybody comes back. And otherwise, I would also like to give our speaker a nice round of applause and thank her for this lovely talk. And then we'll go through questions. Yeah. And you can see all the clapping emojis.
Oh, yes, I see. Thank you so much. Thank you, guys. Do you want me to skim the chat box here, or did you want to navigate the questions?
I'll read them to you. So the first one is from Bruce Remington. Are you going to do ultra high resolution radiography of
foam shock compress? Yes, Bruce, you are on point, man. I do. We should. First step though is so the Ptychography end station, or the instrument we're using right now, doesn't have a dynamic driver. So we're testing out how to achieve high fidelity sub 10 nanometer resolution on the foams in 2 dimensions. We're going to execute this tomography experiment in a couple weeks, as I said, so that hopefully will yield a 3D high-res image of the foam, but that's all static. Then, once we have a good handle on that, we can propose to duplicate that setup at MEC, and but we'll have to get creative, right? Because this is a Ptychography method we're using. Tremendous amount of overlap. Unfortunately, 95%. It turns out that the xFEL beam has quite a bit of different character. The probe is different than a synchrotron probe. Many of the algorithms being used to do the reconstruction have been optimized for synchrotron Ptychography. So there are a couple learning levels of learning that need to happen, but I think you're right that we need to push forward for high-res radiography during compression. You're right. Thank you.
The next question is from Rich London. What is happening in the quest to image biomolecules with xFELs?
Well, that's a great question. So 2 of our hutches here, the Coherent X-ray Imaging CXI hutch and macromolecular femtosecond crystallography MFX or X-ray crystallography hutch, are continuing to do quite a bit of work. It's mostly diffraction based. That's probably what I should say. Looking at the structure, but not necessarily imaging the biomolecules. I think some of that is continuing to be pushed forward, but the techniques for reconstructing in 3D the biomolecules themselves, I think that's still an active area of research with both soft and hard X-rays. But specific examples of that, I am definitely not an expert, so I'm going to couch that answer. So I'm sorry I don't have a specific example for you, but it's certainly being done. In fact, certain aspects of COVID research were done here or in early stages using those. Yeah.
Are there any other questions? Here's one from John Eggert. Does the dynamic Ptychography require a monochromator, or is is SACE mode sufficient?
It's a great question, John. Thanks for coming. So we do monochromatize the beam. So we just use the SASE through a mono. So it also limits our flux a little bit, but it turns out our samples can't take can't take that much beam anyway before they're damaged. So we're not really suffering there. I will say there are novel techniques being discussed for synchrotron-based ptychography using pink beam, and in this way they can basically dump more photons on the sample, and accelerate their imaging mode. I think for us, we're okay taking a monochromatized beam. Some strategies we've considered so that we don't encounter so much beam loss, right? So think about the SASE as it fluctuates. There's going to be intensity drops when it doesn't perfectly match the bandwidth of your monochromatizing crystal. So I believe future work will be looking at silicon monochromators and germanium monochromators to increase the bandwidth so that we have more consistent intensities.
Any other questions? Well, if not, I would like to thank our speaker again and hope to see all you back in a couple weeks.
Excellent. Thanks so much for the opportunity. Take good care.